Hello Pre-Calc PC. Today we are talking about exponential functions and we are going to start with a review of your laws of exponents. So we're just going to run through this first part since it should be primarily review from previous years. So here we have just combining like terms. So 1 plus 1, this will be 2a to the m. When we are multiplying with the same base, we will add our exponents. When we are dividing with the same base, we will subtract our exponents. When we are raised to another power, we will multiply our exponents. In this situation, each of our bases will need the exponents, kind of like distributing but not. 1 to any power is just 1. When we have a negative exponent and we're already in the numerator, the whole thing will move to the denominator. Make sure that exponent changes to a positive. Anything to the 0 power is 1. And this one we won't use so much in this unit, but when we have a fractional exponent, it's the same thing as a root. So a to the 1 over m power is really the mth root of a. All right, so let's practice some of these laws of exponents with these two problems. We will go ahead and we're going to multiply our exponents, but our 4 becomes a 4 to the 3rd. Multiply, so a to the 15th. Multiply c to the negative 15th and give that exponent again. 4 to the negative 4th, a to the 8th, c to the 24th. Now before I evaluate this 4 to the 3rd, what you should notice is that you have the same bases here, so we can just go ahead and add these exponents like we're going to with the a's and the c's. 15 plus 8 is 23. And negative 15 plus 24 is 9. And then finally, we still have a negative exponent for the 4. So the a and the c will stay in the numerator and the 4 will move to the denominator. And it's a 4 to the positive first power right there. All right, number 2, we can go ahead and divide 40 over 55. And that reduces to, I believe, 8/11. Your x's, we have a negative exponent here, so this is going to move to the top. When it moves to the top, it's going to become a positive, and now you will have 14 x's in the numerator. Your y to the 0 is just a 1, so that's gone. Y to the negative 7, it's a negative exponent. It'll move down to the bottom where it becomes a positive 7. And then z, we have a negative 8. It's going to move to the bottom because it's a negative exponent. Make sure you change that exponent now to a positive, and now there are 14 z's on the bottom. Again, that's from adding those exponents. Okay. All right, so next, this is another thing that you worked on last year. This is solving exponential equations where we have the same base. So with number 3, you have a 1 over 3 on one side and you have a 27 on the other. Both of these we can write as a base of 3. Here's how. 27 is just 3 cubed. 1/3 is the same as 3 to the negative first power. So I'm going to rewrite that. And now you have the same base on both sides. 3 to some power equals 3 to some power. So what you can really just do is set your exponents equal to each other. And this negative 1 here is going to distribute to these guys. So that's a negative 2 plus x equals 3. And your x is just a 5. Now, number 4, people want to make this a base of 4, but 4 to no integer power is 8. So the base we actually want to deal with is a 2 here, because 16 is 2 to the 4th, and 8 is 2 to the 3rd. So I'm just going to rewrite this. 2 to the 4th, to the 3x power, 8 is 2 to the 3rd. And again, now that you have your two bases equal to each other, we can just set our exponents equal to each other as well. So this is 4 times 3x is 12x equals 3. And divide, and make sure you divide by the 12, not the 3, and you're going to get x is 1/4. All right, so we're going to skip number 5. We're going to do number 6. That one's a little bit harder, and also to save some time. So this is a little more complicated. The base that we're going to use is a 2 again. So 4 is just 2 squared, right? This guy, 1 over 2 to the negative 2x, well, it's got a negative exponent. I'm just going to move it up, and you already have a base of 2. 8 is 2 cubed. All right, I'm going to simplify a little. 2 times x squared is 2x squared. 3 times 2x is 6x. All right, this situation is different because up here you just had the one base on either side. Now we have all of these 2's. So we still need to use our laws of exponents, and because we are multiplying here, our exponents are going to add. So this is really 2x squared plus 2x for our exponent. Now, once it's written like this, now we can go ahead and we can set these exponents equal to each other. So a 2x squared plus 2x equals 6x. And lucky us, we get to factor. All right, so move your 6 over, those will combine. And then we should be able to factor out a 2x. And then we'll just go ahead and solve for x. And we'll get x equals 0 and x equals 2. And there you go. Moving right along. Go ahead and write this down. What is an exponential function? Well, an exponential function is any function in the form f of x equals a to the x power, but a has to be greater than 0. Okay, we can't have a negative base. And a also can't be equal to 1, because if a is 1, we already discussed 1 to any power is just 1, which would mean you'd have a horizontal line, not a curve. Other things that are true about exponential functions, the domain is always all real numbers because you can plug any value you want in for x here. You can have a negative exponent, positive exponent, doesn't matter. And also when you're creating a table of an exponential function, just what happens here is when you plug in a negative 1 for x, that negative exponent will bring our a down to the denominator, so 1 over a. When you plug in a 0 for x, a to the 0 power, that's always a 1. And when you plug in a 1 for x, we'll just get a. So this will work or be true for all exponential functions. All exponential parent functions, I should say. We're going to skip this part. So we're going to go back to transformations. Transformations never go away. So we're going to graph each exponential function. We're going to list the transformations and then also identify the domain, range, and horizontal asymptote of the function. So this is just the parent function, 2 to the x. So there aren't actually any transformations for this guy. And for values, I'm just going to use -1, 0, 1, 2. And if you want to use 3, we can because the base is pretty small. So when we plug in a -1, our y value is just 1/2. Plug in a 0, 1, plug in a 1, 2, so on and so forth. Okay, and you can just go ahead and you can plot these points for me. And this is what your curve looks like. This guy will have a horizontal asymptote at y equals 0. And that is your standard horizontal asymptote for an exponential curve, unless you have some sort of vertical shift. And then your horizontal asymptote will be based on where the shift is. Domain, we already said for exponential functions is all real numbers. Range, because there is no vertical shift here, it's just based on the horizontal asymptote. And so we're going to say range is going to be 0 to infinity, or you could say y such that y is greater than 0. Okay, whatever notation you prefer to use. All right, so that's a parent function. Now let's actually do one with a shift. Letter B, we are going to graph from f of x equals 2 to the x, which means that's your step 1. This is your parent function. That's what that's telling you. This right here would be the same as 2 to the negative 1. So this is really 2 to the negative x. That is our step 2. And what that means, if you recall, is that x is being multiplied by negative 1. It also means that we are reflecting over the y-axis. So let's see how that works. 2 to the x, we already have this table right here. I'm just going to go ahead and, I don't know if I can copy it. Oh well, I'll just rewrite it. We'll just do a few of the points. So let's put the parent function on there first. Just quickly re-graph the one that we just had. And you don't have to use all of the new points if you don't want to. Okay, so that's the parent function. So what's happening is we are multiplying our x coordinate by negative 1. Okay, because it's negative x. So all of your x's are just going to switch signs. Your y's are staying exactly the same, and now I'm going to regraph. Positive 1, 1/2, 0, 1, negative 1, 2, negative 2, 4. And you can see that it is a reflection over the y-axis. Because we did not have any vertical shifts, your horizontal asymptote is still at y equals 0. And we should have that graphed, so go ahead and put it on your graph. Our domain for exponentials is always all real numbers. And our range, again, because we didn't have a vertical shift, is just based on our horizontal asymptote here. So we're going from 0 to infinity, or you could say y such that y is greater than or equal to 0. All right, one more of these. We're going to jump to letter D. This one's a little more complicated. I want you to change the problem so it's written as negative 4 to the x plus 3, which would just be when you do the negative 2 squared, you get negative 4. But again, we're going to use y equals 2 to the x as the parent function, just like we did in the last problem. So step 1 is just our parent function. You can use, I used y. What did I use in the last one? I used f of x. Okay, I'll keep using f of x. So there's your parent. All right, so now this is where your order matters. So think back to what we did in chapter 2 with your order of transformations. There isn't a horizontal shift. That would be if you had like some plus 3 up here with your x, but you don't. But what would be next is this 2 to the 2x. Because that is your horizontal compress, which means we are multiplying x by 1/2. Remember, with our horizontal stretch compress, we're multiplying by the reciprocal of that number with x. Next would be your vertical stretch compress reflect, which is this negative right in front. And what that is doing is multiplying your y by negative 1, which is reflecting over the x-axis. Notice the difference here. The negative is in front. That's multiplying y by negative 1, whereas our last problem, the negatives was with the x. That was multiplying x by negative 1. All right, and then finally the plus 3, which we know from transformations means we're going to move up 3. This also means that our horizontal asymptote will be in a different location this time. Okay, so I'm just going to go ahead, I'm going to put my original, some points from my original parent function. So again, this is 1/2, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4. And I might as well put this as well. And now let's just graph our parent function. And let's dot that. And you don't have to put the horizontal asymptote yet because we don't have our final answer. Just make sure you have your horizontal asymptote of your new function once you've graphed it. Okay, so now we're just going to run through these things here. We're multiplying x by 1/2. So all of these guys are multiplying by 1/2. And for me, I'm going to actually write it out. Okay, I've multiplied x by 1/2. I am multiplying y by -1. So now I'm going to multiply all my y's by -1. And then I'm taking all of those and I'm going up 3. All right, so these guys are all going up 3. So that's going to be up 2.5, up 3, that's 2, up 3, that's 1, up 3, that's -1, up 3, that's -5. So this is now my new function that I'm going to graph. So I'm at -1/2, 2.5, 0, 2, 1/2, 1, 1, -1, 1.5, -5. And we should know that because our horizontal asymptote originally was at 0, but we moved this whole thing up 3, you're now going to have a horizontal asymptote at y equals 3. And that is when you need to draw it because it's going to assist you to draw your final answer. Okay, so horizontal asymptote is at y equals 3. Domain, guess what? It's still all real numbers. Range, a little different this time. Make sure you look at the picture. We are going from -infinity to 3. Or you could say y such that y is less than -3. One more thing to talk about. E, the exponential function. So E we can find on your calculator. It's actually in 2 places. If you just want E itself, you can do second and then division, which is right there. If you want to raise E to a power, it's right over your natural log, and it pulls up a power, so you can do that if you want. So either one works. So we are going to graph this function. And really, it's still an exponential, okay? It's still an exponential function. It's just E, your base, is a decimal. Okay, but your transformations are still going to be the same. So we would start with e to the x. That would be your parent function. And then, if you notice, this one has a horizontal shift, so that would come next. So that would be a right 2. Okay, and then we have this negative out front. That is multiplying your y by -2, or excuse me, by -1. I'm still stuck on that 2. Multiply your y by -1, which means we are reflecting over the x-axis. Okay, so when you make your table for this, it's a little more complicated. I'm just going to use 0, 1, and 2. It's going to be easier. And again, we're plugging this into the parent function, okay, this guy right here. So e to the 0, well, that's 1. E to the 1 is e, And e to the second power is e squared. And if you notice, I already typed those into my calculator. So e is, just for graphing purposes, I'm going to say a 2.7. And e squared is, we're going to say a 7.4. Again, just for graphing purposes. So that's the parent function. 0, 1, 1, 2.7, 2, 7.4. All right, and again, there's no vertical shift, so at least originally you have a horizontal asymptote at y equals 0, which you can either choose to graph or not. All right, so that's e to the x right now. And if you type e to the x into your graphing calculator, it will look just like that. So now let's go ahead and let's do our shifts. So right 2, that's your x coordinate that's changing. So all of these guys are just adding 2. And then we're multiplying y by -1. So all of these guys are just becoming negative. And now we can graph it. 2, -1, 3, -2.7, 4, -7.4. And again, there's no vertical shift. So our horizontal asymptote is going to remain at y equals 0. Okay, so you can see it's basically a reflection over the x-axis, but again, it's been shifted to the right too. And that is your graph. So I hope you have a great day. Let me know if you have any questions. Bye.